Now there's something even cooler, and that is, remember, we're trying to maximize the variance along that dimension. So now we determined that that dimension that maximizes the variance, it must be an eigenvector, right? So what is the variance along that eigenvector? Let's actually compute the variance. Again, E is our eigenvector. We're projecting all the data points to that eigenvector using dot product. And now we just want to look for the variance of the projections. Okay, so the variance is going to be that. These are the projected values, subtracting the mean, squaring it, summing it up over all the instances in the data. And again, I'm going to say that that mean is going to be 0. Wait, I actually promised that we'll... Okay, so let's actually show that it is 0. Right? It's not very hard. What is the mean? We're looking for the mean of these points, so it's the mean of the projections, right? So that's our mean. We're going to sum up over all instances, 1 over n, and inside is the value of the projection. Now the value of the projection is just the dot product between the ith instance xi and our eigenvector e. Right? We have two sums. We can change the order of summations. If I move that sum over i's inside, look at what I get. I get ej multiplied by, in parentheses, the sum over all i's, so the sum over all instances, the value of jth attribute summed up over all instances divided by n. Right. That thing inside the parentheses is just the mean of the jth attribute before I did the projection. And that mean must be 0. Why? Because I centered the data. To begin with, I subtracted the mean from every single attribute. Right? So that mean is 0. When you multiply 0 by any vector, you're going to get zeros back. So if the mean was 0 in the original space, it's still going to be 0 in the projected space. That's the way to take it out. Okay. So mu is 0, so my variance is just going to be that quantity over there. Right. Now, I'm going to take it, rip it up. So I have this quantity squared, so I'm just going to take it and multiply it by itself. That's the same thing as squaring it. But in order to avoid confusion, I'm going to use different subscripts for the two sums. So these are exactly the same sum. All the terms are identical, only here I'm using a's to denote the attribute, and here I'm using j's to denote the attribute. Everything else is the same. So multiplying these two things is the same thing as squaring one of them, because they're identical. Okay. Now, once I've written it out like that, I can start moving the summations around again, right? So the summations can always be taken outside. So what I'm going to do is I'm going to take the sum over j's and the sum over a's. I'm going to move them all the way outside, and what I'm going to leave inside is the summation over i's. Right? So the terms that depend on I are xij and xia. So I'm going to leave them under the I summation. And what's going to be outside of that is ej and ea. Okay? Pretty simple manipulation. Again, you stare at this formula, you realize that this is something that we've seen before. That is the covariance between attribute A and attribute J. So it's just an entry in the covariance matrix. So what I'm doing is I'm summing up over all attributes A, over all attributes J, the covariance of A and J, multiplied by the jth component of an eigenvector, multiplied by the ath component of an eigenvector. Okay. Now look at the inside sum. What I have here is, for all J from 1 to D, I look at the covariance of A and J. So that is the row of the covariance matrix. And I'm taking that row and multiplying that by the elements of the eigenvector. So I'm doing a dot product between a row of the covariance matrix and the eigenvector E. And because it's an eigenvector, I know what that thing is going to come out to, right? Because eigenvectors, when you multiply them by covariance matrix, you get something very specific back. You get the eigenvector back. Right? So multiplying it by a row, by the eighth row of the covariance matrix, gets you back just the eighth component of your eigenvector multiplied by the corresponding eigenvalue. So that's the property of eigenvalues and eigenvectors that we had from the previous slide. Okay, so now I can replace this whole inside summation with lambda times EA. And now what I have is the sum for attribute A, for all attributes from 1 to D, lambda times the value of EA times the value of EA. Right? Take lambda outside, EA times EA, that's EA squared. So I have the sum of the square elements of the eigenvector, and my eigenvector is unit length. Right? So the sum of squared elements is just going to be 1. So what I'm left with is lambda. Lambda is the eigenvalue that corresponds to the eigenvector. And what we've just proved is that thing in the beginning, that's the variance of projected points along the eigenvector. And we just proved that that's going to be the eigenvalue. So you get two cool things. One, the eigenvector is where the data is spread out the most, and the amount of spreading is nothing but the eigenvalue. That's pretty cool.